Hi guys, and welcome to our video today. So this tutorial today is going to be about LCD displays. So I'm pretty sure most of you have already used one of these things before with your Arduino. And while these have become relatively inexpensive over the last few years, one problem remains. They have a parallel interface. So what that means is you need a lot of pins to drive them. Typically you'd need about 4 pins for data, plus 2 or 3 pins for control, and obviously your supply voltages. So if you're running on an Arduino Uno, you'll probably run out of pins. Another issue with this type of screens is that if you decide to run your Arduino on a low power application, say 3.3 volts or from a lithium battery, then you'll find that these displays do not work, because they are mostly available in 5 volts versions only. So, having these problems in mind, I decided to build myself an interface board, which is this one in here. And it's actually very simple. So what this does is, rather than using the parallel interface to connect to the display, what I do is I modify the standard library, and now I send the data via shift register. So as you may notice, I am using all the pins of the display, which is a rather unusual configuration. Typically these are driven using 4-bit mode. This board in particular uses 8 bits, and the reason for so is to actually add up on speed. Because when you transfer data to these displays, the controller accepts a 4-bit mode in which you send the first 4 bits of data. Then you have to send another command, wait for the LCD controller to stabilize, and then send the other 4 bits of data, and then send another command. And obviously this takes longer time than if you send the 8 bits all at the same time. And the same is true for the processor, because this is an 8-bit processor. So what you're going to do is you're going to spread the instructions into 2. So you're basically taking half of the capacity, because you have to do 2 8-bit instructions even though you're only using 4 bits. So not very efficient. So I said, okay, if pins are not an issue, then maybe I can speed up things a little bit. This was created for an application I had where I had to do a refresh rate of about 50-60 Hz for the display, and at the same time I needed to have time to do some other tasks. So I really needed the LCD interface to be very fast, no delays, no nothing. So the idea was to come up with a shift register, drive the display directly in 8-bit mode, and the control bits on this particular version are actually triggered by hardware, by the microprocessor. So rather than sending another full SPI instruction with another 8 bits, which would take time, I actually toggle them by hardware. I also have another version of this and uses the same shift register without the hardware toggle bits, and this makes it more compact. Essentially, if you're already using the SPI for some other tasks, you're only going to need one more wire, which is shift select, to select this controller. If you're using the 8-bit version, which is the fastest one, you will need 3 wires. You need enable, read and write, and you're gonna need the shift select as well. So 3 bits. So let's do a demonstration. Basically the controller has 8 pins, 7 are being used. 5 of them are taken directly from the ISP bus, actually 4. So you take the supply voltage, and you take the system clock and the master out slave in data, which sends the data to the LCD, and then you have another 3 bits which you can choose somewhere on the hardware, so you can actually program these on the software. So if we connect the LCD screen, and then we connect the display to the Arduino. CAMS is rebooting, so it's gonna make this is just because the lines on the SPI are obviously floating. Once the Arduino boots up, then we have all the data on the display is relatively fast. This Arduino in particular is being fed with 3.3 volts. Now I can also feed it with 5, just using this jumper in here. So you're gonna notice that the LEDs are gonna stay brighter. That's 5 volts, that's 3.3 volts. You can see that there is absolutely no change on the LCD. I could reset it at 5 volts and it's still going to operate. Reset at 3.3 volts, still works fine. Another possibility, which more often is needed, is to supply this from a single lithium cell, which is roughly 3.6 volts. So that can be done as well. Switch off the USB, power up the cell, and voila. Basically the controller has got a built-in DC-DC converter, so it takes anything from roughly 3 volts to 5.5 and it outputs it to the LCD. We've got a contrast potentiometer in here as well. We've got a jumper to enable or disable the backlight, and you can make one of these yourself for rather pounds, more or less. There are some SMD components because obviously I wanted to keep the format as compact as possible. The shift register, I use the standard DIP one, and here are our schematics. So it's very simple. Basically, one of the sections is the shift register interface, and the other section is simply a boost converter operating with an MC34063. This is relatively inexpensive, you can get them for 40 pence. There is an SMD inductor on board, which is this one. It cannot provide a lot of current, typically about 10-15 milliamps maximum, so the backlight needs to be limited with the resistor. Obviously we could make higher capability, but the inductor would be larger, so it really depends what your needs are. Basically that's it. We have an LCD using only 3 pins if you're already using the SPI for some other task, and you can power it from a single lithium cell. I'll post a link to this on the Arduino forum where you can find the schematics and also some demo code for the LCD. Alright, see you later guys, and thanks for watching.